Swayam Prabha. Digital India. Educated India.
Proof of this Sherman-Morrison-Woodbury formula that's given in this slide. I'm not going to go over that, but I'll show you. I will tell you what I'm trying to do. So that's where the proof comes in. So I'm just going to give you a heads up. So A and B are two matrices, non-singular. C and D are matrices n by k. With me? So consider a matrix lambda. I am building out of A, B, C, D. Everybody with me, please. Now look at why are we talking about this? I am talking about the last formula. There is A, there is B, there is C, there is D. Okay. So I am considering this new matrix is a block structured matrix. I want to be able to compute the inverse of lambda. I don't know what it is. I assume that it has a block structure PQRS. My job is to be able to, given A, B, C, and D, my job is to be able to find PQRS. Do all of us get that, please? That's the problem I want to talk about that. Now, if this were to be the inverse of lambda, I have to compute the product of the two. The product must be identity. That's the definition of inverse. Everybody. So the product is given by these matrices, and that must be this. You can compute the size of the matrix, and that's what that one is. So what is that I would like to do now? Equate the two elements. AQ plus CS must be 0. D transpose P plus BR must be 0. AP plus CR must be IN. D transpose Q must be equal to this. So we get 4 relations. We have to manipulate these 4 relations. I'm giving you an idea of the proof. So these are the 4 relations you get. Now let's go back now. So AP plus CR must be equal to identity, and that gives you Q must be this, R must be this. So equating the diagonal elements and using 1 or using these properties, I can now see AP plus CR is IN. So what is that now I can do? This implies P is equal to A plus CB inverse D transpose inverse. Likewise, this is IK. Again, I want to be able to recognize I am computing S, I am computing P. I am using all these relations and using this to get this. Everybody please? I'm going to ask you to verify this. I'm giving you the proof. I simply want you to be able to plug and chug and verify indeed that's the formula. With me? That's right. Therefore, lambda inverse is given by that. So I'm computing P, PA plus QD is IN, and P is given by this formula, which by using N I get this. All of you? That's right. I don't think it's wise for me to be able to go through every little step, but I have given you the entire solution. So what is involved in here for you to be able to work through? If you work through this, you become better and better in matrix algebra. So that's the idea of that. So please verify this proof of the Sherman-Morrison-Woodbury formula. So let me go back and summarize the whole thing. Sherman-Morrison-Woodbury formula has several forms. I took the most general form and I gave you a proof of that. So that proves. Now what is that I need to do? So this is the form we already got in the previous slide. Now I am going to set B is equal to IK. I get the formula C. When K is equal to 1, I get the formula B. When A is equal to IN, I get the formula A. Everybody with me, please? So I have 4 formulas A, B, C, D. I showed you the method of proof for D. Are you all with me? That's right. Then I showed you how I can get all the results by specializing choice of B. You all have an aha here. That's right. Now I am going to talk about another operation which is called the Moore-Penrose or generalized inverse. I don't know how many of you have heard of that. That's right, good. It often occurs in the context of least squares analysis. We will talk about least squares analysis in great detail in the next module. We define the inverse of a square matrix. Again, mathematician asks the following question. If you can define the inverse of a square matrix, is there a concept of inverse of a rectangular matrix? That's called the generalized inverse. So here I am going to be talking about inverses of generalized matrices. So if A is a square matrix, I denote the inverse by A inverse. If A is a rectangular matrix, I am going to denote the generalized inverse by A plus. In some textbook they will say A dagger. In some textbook they will use A star. I want to be able to use a notation which is different from here, anything. So I prefer A plus. A to the power of minus 1 is inverse in the regular sense. A plus is the inverse in the generalized sense. Everybody? Hey, what is the notation? Your notation, there is a concept, there is a notation. For example, you need a name. There is a proverb. The rose smells the same by whatever name you call. The properties of the flower rose is not going to change if you change the name. Rose is a rose is a rose by whatever name you call. You need a label, you have a name, right? But your property is not dependent on what your name is. So I want to be able to ask you to dissociate the label from the basic concept. If you understand that, you can use any label so long as you refer to the concept by that label. That's an important thing. So there's a whole family of generalized inverse. That's not one generalized inverse. With me? The most useful of the generalized inverse is called the Moore-Penrose generalized inverse. So to say generalized inverse means a whole host of generalized inverses. To talk about Moore-Penrose inverse is a specific family of generalized inverses. There are books written on simply generalized inverse of matrices, a 300-page book on generalized inverse of matrices. You can do generalized inverse for one semester, in a one semester course. Where they will talk about all different forms of generalized inverse. I am now going to talk about only one of them. A plus is called the Moore-Penrose type generalized inverse if it satisfies 4 properties. This is how they defined it. A plus A is A. Oh, before I go further, please understand the generalized inverse of a m by n matrix is n by m. With me? The generalized inverse of a m by n matrix is n by m. So A plus A must be equal to A. So how does this work? This essentially works like this. Now let me. So A plus A is equal to A. So how does this go? That means A plus A behaves like an identity. A plus A, this behaves like identity. That's why it's called generalized inverse. With me? This behaves like identity, this behaves like identity. A plus is A plus. A plus A transpose is A plus A. So what does it mean? The product of A plus is symmetric. Now what is the size of this matrix? This size is m by m. Are you with me, please? Okay, A plus transpose is A plus transpose. That's also symmetric, because if a transpose of a matrix is itself, it is symmetric. And what is the size of that? N by n. So it looks as though they are similar to the Gramian that we saw, but they are not Gramian. It is one of the two matrices. It's the inverse, the generalized inverse of A itself. So A plus. So we say, given a matrix A, it has a generalized inverse A plus if and only if it satisfies all the four conditions. Then we say that matrix that satisfies all the four conditions is called the Moore-Penrose generalized inverse. In fact, that's a very clear-cut, beautiful algorithm to compute the generalized inverse. Are you with me? I gave you an algorithm for computing the determinant. We did not talk about the algorithm for computing the inverse of a matrix. That's another topic. We have not touched it yet. We are only probably defining everything else. We will talk about the algorithm for computing the generalized Moore-Penrose generalized inverse when we do modeling. A is a full rank matrix. That's what I'm coming to next. A plus can be expressed explicitly. Do you see that, please? If A is a full rank matrix means what? If M is greater than N, the full rank matrix means the rank of matrix is N. So when the matrix has a rank N, its inverse can be expressed A transpose A inverse A transpose. If M is less than N, the rank of A is M. In that case, the generalized inverse can be expressed as A transpose A transpose inverse. This is the basis for the least squares theory. In the very first lecture, I talked about the method of least squares was introduced by Gauss. In Gauss's time, matrix theory was not developed this much. But Gauss did not need matrix theory. He was one of the brightest mathematicians of all times. So he developed the theory based on the principles of calculus known at that time. Please understand, 1400, 1500, 1600, 1700s. With me? Those days. When M is N, A is non-singular, the generalized inverse is the regular inverse. In that case, A plus A is equal to A plus is equal to identity. This is exactly what Moore and Penrose asked for. How do I define the inverse of a matrix for an inverse of a rectangular matrix that will become the inverse of a square matrix when M is N? M is equal to N. With me? And how do I generalize this? So this is the specialization, this is the generalization. The specialization was known for a long time, they generalized it. Are you all with me? Now I am going to talk about another role of matrices, which is matrix as linear transformation. So what is that we have accomplished so far? So far, we consider matrix as a class of object, like vectors, like numbers. We studied operations of this matrices and various properties and special types of matrices. That's what we did. This is a general pathway in every algebra. Are you all with me? That's right. So now I'm going to talk about matrices as a linear transformation. Let A be a M by N matrix. So what does it mean? I have a space of Rn, I have a space of Rm, y is equal to A of x. If A is M by N, x has to be a n vector. So x belongs to Rn, y belongs to Rm. So it associates a vector x with a vector y. It transforms the vector x to transforms the vector y. Vector x in Rn, vector m in Rm. So that's called transformation. This is called linear transformation. Linear, nonlinear, what is the difference? Everything occurs in the first degree is generally linear. With me? So Ax occurs as the first degree. So Ax to y. So x is n by. n vector, y is a m vector. A is called a linear transformation from Rn to Rm with the following properties. What are the properties? A of x plus y is A of x plus A of y for all x and y in Rn. A of little a times cap x is equal to A times Ax. That means if I multiply the vector by a constant A and then transform it, is equivalent to multiplying the transformed vector by A. Now there are two important concepts. One is called the range, another is the null set of A. What is called the range of A? Please understand, the A takes the vectors from x to y. So if I pick a particular x, I get a particular y. If I change the x, I get another y. So if I change x over all of Rn, I'm going to get a collection of vectors in Rm. So the range of A is the set of all vectors in Rm such that they occur as Ax for all x belonging to Rm. That means if this is Rm, this is called the range of A. It may not cover the whole thing. So the range of A is a subset of Rm. Now there is another thing called kernel of A. Kernel of A consists of all those x in Rn so that Ax is 0. So the kernel of A is here. This is called the kernel. So kernel of A means what? If I multiply a vector in x by A, I get a 0 vector. Therefore, the kernel of A is also called the null space of A. Why it is null space? It annuls. Multiplying any vector in that space creates a 0 vector. Creating a 0 vector is called annulling. So that is the space of vectors such that if I multiply them by A, I get 0 vector. If I multiply every vector in here, I get the vector in here. So this is the range of A. Range of A. So these two things are very fundamental. Range tells you the reach. Null tells you your path being annihilated. Ker is also called kernel. Null set, kernel are two important concepts. Now I'm going to give you a couple of operations. Are you with me? There's no notion of that. Now I'm going to talk about the examples of operation. Orthogonal matrix, I already talked about. You remember that? Q. Orthogonal transformation. So I'm now talking about orthogonal matrices as transformation. Why is that? Let's look at this now. Suppose I have a unit vector. I need not have unit vector. I suppose I have a vector, x, which is x1, x2. Consider the matrix Q, which is equal to CS minus SC. Consider the vector y, which is equal to Qx. And what is that? That is equal to x1c plus x2s. The second component is minus x1s plus x2c. All of it me? So what does it do? The y is somewhere here. Sorry, the y is somewhere here. Now what is the relation between x and y? That's what when Q is orthogonal. That's a question I'm going to ask. So y is equal to Q of x, Q is orthogonal. So let us compute the square of the length of y. You all remember square of the length of a vector is simply that it's transposed with itself. All of it, please? That's right. Therefore, y is equal to Q of x. The square of the norm of x is equal to Qx transpose times Q of x. transpose of the product taken in the opposite direction is a Q transpose, X transpose Q transpose QX. But QQ transpose being orthogonal is identity. So this becomes X transpose X, and that is equal to square of the norm of X. Wow. The square of the length of X is the same as square of the length of Y if I multiply X by Q to get Y. If two vectors have the same length means what? They lie in a sphere whose locus is simply the radius, which is given by the length of the vector X. So what does this tell you? Orthogonal matrices simply rotates the vector without changing the length. So in principle, if you multiply a matrix by if you multiply a vector by a matrix, two things happen. It rotates and it shrinks or elongates. Rotation and deformation. Everybody? Rotation and scaling. Instead of calling deformation, I was called scaling. Scaling is equal to multiplying a vector by a constant. Rotation by an angle. The angle of rotation could be either clockwise or anti-clockwise. With me? That's right. So what is that we have learned now? If you multiply any vector by an orthogonal matrix, the resulting transformation, the resulting transformed vector Y, its length must be the same as that of X, only the angle between X and Y changes. That means orthogonal transformation as linear transformations are basically rotations. Now, have you seen in computer graphics, you rotate a picture. In a camera, you say rotate. Do you do that? That's right. So what is rotation? It's an orthogonal transformation. Matrix. So let's talk about graphics. What is graphics? Graphics is essentially three-dimensional. Computer graphics are either two-dimensional or three-dimensional. Everybody? So what is the mathematical guts of computer graphics? Linear algebra. So what are the operations we want to do? I want to translate an object. I want to shrink an object. I want to scale an object. I want to rotate an object. So these are the operations that people in graphics need. I'm talking about rotation as a transformation, which can be accomplished by orthogonal matrix. So you also learn something about geometry along with that. And it is to be expected. Why? Matrix algebra is a form of analytical geometry. It's purely geometric in nature. So here's an example of a transformation. I'm combining two concepts, scaling, rotation. Rotation is obtained by orthogonal transformations. Now I'm going to talk about coordinate transformation. Oftentimes we need to be able to change the coordinates. Everybody with me please? To be able to make calculations simple. So I'm now going to talk about standard basis. What is the standard basis? E1, E2, En. So what is EI? EI is the ith coordinate basis where the ith component is 1, everywhere else is 0. In the 2D, we have already E1 which is equal to 1, 0, E2 is equal to 0, 1. Everybody. So, in n-dimensional space, we already saw must have n bases. Let the same space contain another basis. I want to tell you that the same space can be done in two different ways. So let's look at this now. If I have a two-dimensional plane, I can have the standard basis. Of course, I can also do arithmetic in this basis. If two basis vectors are orthogonal, that's called orthogonal basis. If two basis vectors are not orthogonal, that's called oblique basis. I can do arithmetic. All I need is a system of two linearly independent vectors. If they are orthogonal, the calculation gets simplified. So given any two linearly independent vectors in 2D, they constitute a basis in 2D. So how many different possible ways of getting a basis in 2D? Infinitely many. If 2D allows infinitely many bases, Rn allows infinitely many bases. So let this be the standard basis, this be a new basis. I did not specify what that basis I want this to be. It's a new basis. So I am now considering a matrix whose columns are the standard basis, which is capital E. I am going to consider a matrix G whose columns are the vectors G, with me, new basis. So every vector in the new basis, please understand, they all share the same space. So every G must be expressible uniquely as a linear combinations of my old basis. So that's what this one is. GI must be representable as T1i-E1, T2i-E2 plus Tni-En. Are you all with me, please? That's right. So this essentially tells you the set of all vectors G1, G2, Gn must be expressible as E1, E2, En plus this matrix. If you multiply E1 times T11, E2 times T21, E2 times Tn1, I get G1. That's the definition of GI. So GI, this definition leads to this matrix equation. This is for one I, this is for collectively every I. Everybody. Are you all with me now? So this is the matrix G, this is the matrix E, this is the transformation T. This is the transformation T. We will have occasion to talk about change of basis later, and this is exactly what happens in here. I hope the geometry is clear. So the coordinate transformation, this essentially tells you G is equal to E times T. Sorry. G is equal to E times T, where T is non-singular. It's a non-singular transformation. So now I'm going to talk about, let U be a vector in Rn. The vector U in Rn can be expressed uniquely using the basis capital E. So there must exist a vector X such that U is equal to Ex. Everybody please. Every vector in Rn has a standard expansion in the standard basis. Everybody. So that's equal to E1 x1 plus E2 x2 plus EM x1 in B1. Now the same vector U must have a representation in the new basis G. Everybody with me please. Only my frame of reference changes, my object does not change. It's like in physics we are talking about velocity with respect to a moving platform or velocity with respect to a fixed point. That's essentially the kind of reference. So U can also be expressed as G times X star, which is G11 X star, G22 X star, Gn X star. So X star is a vector of coordinates in the new basis, X is the vector of coordinates in the old basis, both of them are representing the same point. Think about it now. Your grandmother calls you by some name, your mother calls you by some name, your friends calls you by some other name, right? Come on guys. Your mother has a nickname for you, your grandmother has a nickname for you, your friends have a nickname for you, then you have your name. You are the same object. The same object can have several labels. So I have a same point, one label is X, another label is X star. I am trying to find the relation between X and X star, knowing that X is expressible in the standard basis, X star is expressible in the new basis. And if I know the relation between the bases, I should be able to express the relation between X and X star. Are you all with me now? That's the idea. Ex is equal to Gx star because they represent the same point. Therefore, X is equal to E inverse G. I multiply both sides by E inverse on the left. But E inverse G is equal to T because that's what is given in here. Therefore, coordinates of U in B1 and B2 are related by X is equal to Tx star. So if I know the transformation of the basis, I do know the transformation of the corresponding vectors. So that's a very fundamental and important role. So I can think of matrix as an object. I can think of matrix as an operator or an operation. An operation is defined by its action. How do you define a hammer? I can only hit it. So there is a proverb in English that goes by the following way. If hammer is the only tool you have, every job looks like a nail. It's a very important proverb. If hammer is the only tool you have, every job looks like a nail. Why? The action of a hammer is only to hit. I can only hit a nail with a hammer. With me, please? So there are multiple things. You need more tools to be able to do many things. If hammer is the only thing, you can only hit. That's one way. Another way is transformation from one basis to another basis. Operator, T, operations by action. You always define an operator by its action. All of you? That's right. So we talked about matrix as an object. Now we are talking matrix as an operator, and we are trying to define the operator by its action. You all see the difference, please? That's right. Now I'm going to talk about a class of transformation called similarity transformation. Let x and y be in Rn. They are in the standard basis B1. That means I am considering a standard basis B1. I am considering two vectors represented in the standard basis. Let A be a linear operator. In the previous case, I called it T. Now I am calling it A. Y is equal to AX. You remember that now? So I have Rn. Here is X. Here is Y. Both of them in Rn. And A transforms that to Y. An operator is defined by its action. So let T be a transformation of the basis B1 to a new basis B2. So this Rn has two bases. One is B1, another is B2. Are you all with me now? So now let's talk about this now. X and Y are the coordinates of points in B1. I'm changing the coordinate B1 to B2. A is an operator from X to Y. I can represent X in B1, I can represent Y in B1, I have already done. I can now represent X in B2, Y in B2. So if I change the representation of X in B2, if I change the representation of Y in B2, how does the operator A changes? Are you with me? In the new basis. The operator A is defined in the old basis. If I change the basis, I need new expression for the operator in the new basis. That's what we are going to be talking about. X star, Y star be the representation of X and Y in the new basis. So the transformation, so A is a transformation that transforms X to Y. T is a transformation that transforms the basis B1 to basis B2. We are talking about two different types of transformations simultaneously. With me? So X is T X star, Y is T Y star. T X star, T Y star, we already know from the previous step. Do we? That's right. So let Y is equal to A of X. So now what is that we say? Y is equal to T Y star. Y is equal to AX. With me? So that becomes ATX star. I hope you are all with me now. Here I am plugging this in here. That's what this one is. Now Y star is equal to T inverse ATX star. See, look at this now. So I have Y is equal to Ty star. Therefore, Y star is equal to T inverse Y, and Y according to this is T inverse ATX star. So this is equal to T inverse ATX star. Everybody. So what is that now? If you X star is same, Y is also same. So I'm looking at a new way of mapping in the new basis. And what is this operation corresponding to this? T inverse AT. How many of you are with me? Please. I know quite a few things, but I don't know how to read your mind. So if you have doubt, you may have to ask. So A is an operator that maps x to y in the standard basis. I change the basis from x to x star, B1 to B2. Every matrix has a unique representation on a given basis. Why is that? Let's go back. G is the new basis, E is the old basis. I can transfer E to G using the transformation. The transformation depends on the original basis. The original basis is the one that I'm going to transfer. Therefore, representation depends on the basis. So, the matrix A and T inverse AT, T inverse AT, what do? They map the same point to the same point as A does. A transfers x to y in the old basis. T inverse AT transforms x star to y star in the new basis. They do make the same action. Therefore, these two matrices are called similar matrices. And this transformation of making A to T inverse AT is called the similarity transformation. And what is the importance of this? If you change the basis, all the matrices change. If you change the basis, matrices have to be changed, and that change in matrix can be captured by this type of transformation. That type of transformation is called similarity transformation. Similarity transformation. Are you with me? That's right. The another transformation is called congruence transformation. If A and B are two non-singular matrices, the transformation to A is equal to B transpose AB is called a congruence transformation. So, two things now. A, T inverse AT, B transpose AB. This is called similarity transformation. This is called congruent transformation. With me? I'm not going to talk too much about congruent transformation. Maybe when the application comes in, we will talk about that. Congruent transformation occurs naturally. Similarity transformation occurs when you change the coordinate basis. And that tells you a couple of interesting things. Matrix can be thought of as an operator. The representation of the operator depends on the basis. So this is one representation of the same object called the matrix in the old basis. This is the new representation of the same object to the new basis. So change of operators, representation of operators, and the dependence of representation on the basis. That's what we talked about. Are you all with me? Next one is called the adjoint operator. If A is an n by n matrix, A can be thought of as a linear operator in Rn. That's what we talked about, right? Now I'm going to define a close cousin of A called adjoint of A. I'm going to denote the adjoint of A by A star. Now look at this now. A transpose, A inverse, A generalized inverse, now A adjoint. I'm creating newer matrices from older matrices by defining newer operations and so on. So how do I define the operator A star, adjoint operator, A as an operator? So if I'm given two vectors x and y, if I compute the inner product of Ax to y, so let's look at this now. This is x, this is y, Ax is this. If you multiply a vector by a matrix, it becomes a new vector. So instead of taking inner product of x and y, I am taking the inner product of Ax and y, where A is a transformation. All of it may? If there is a matrix A star such that this inner product is the same as x with A star y, that's called that. Such an A star is called the adjoint of A. Now I'm going to give you a meaning of the adjoint. Adjoint is very closely related to the transpose. So let's look at this now. How do I compute inner product of Ax? inner product of Ax is Ax transpose Y. Everybody? That's equal to X transpose A transpose Y because the product of the transpose is taken in the reverse order. So this can be written as X transpose AY. This can be written as X comma A transpose Y, and that looks like this. So A star is A transpose. So one way to look at adjoint is one interpretation of adjoint is the transpose of a matrix is called the adjoint of the matrix. Everybody? Adjoint is essentially defined by this equality. So it follows that adjoint is a transpose. And what are the properties of adjoint? If A is a symmetric matrix, A is equal to A transpose. If A transpose is the adjoint, A transpose is equal to A is called the self-adjoint. So for symmetric matrices, since A is equal to A transpose and A transpose is called the adjoint of A itself its own adjoint. That's called self-adjoint. Everybody, that comes essentially from symmetric matrices. Now I have several properties. Adjoint of an adjoint it's A. A constant multiple of A, adjoint of a constant multiple of A is A times the adjoint. A plus B adjoint is A adjoint plus B adjoint. AB adjoint must be B adjoint A adjoint. If A inverse exists, then adjoint to the inverse is the inverse of the adjoint. You can verify these properties by replacing adjoint by transpose. So in the case of finite dimensional space, adjoint and transpose become equivalent. In the general space, adjoint has a different property. With me? That will take us deeper into other aspects of linear algebra. But for the time being, I want you to be able to understand there is an operation called adjoint, which is equivalent to the transpose.